right, so we've been talking about transport across cell membranes. Last time we talked about diffusion, or simple diffusion, which was where solutes just went from higher to lower concentrations across a membrane. And we actually did that in the lab. We did it with the starch and the iodine solution, and we looked at how the starch could not pass through the baggie into the solution outside. It was too big to pass through that fake membrane. We were sort of using that as a representative membrane. But the iodine, the Lugol's iodine solution, was able to pass through the membrane from high to low concentrations, and then it reacted with the starch inside. We also briefly talked about osmosis, which is the movement of water across a membrane, also from high to low concentrations. Now, water can flow through the membrane fairly easily because of these special proteins in the membrane called aquaporins that let water sort of pass through. And so, here's the thing. Most solutes cannot pass through the phospholipid bilayer. Ions can't pass, large things like sugar or protein can't pass, very few things can pass. But water, because of the aquaporins, and the phospholipid bilayer also allows a little bit of it through, water can pass. So a lot of times, what's going to happen to a cell will depend on the water concentrations on two sides of the membrane, not so much which way the solutes are going to go, because they may not be able to pass at all, but the water. So checkpoint question, this is what we're going to be looking at, is trying to figure out something like this. It says, predict the movement of water between two solutions, a 0.5 molar sucrose solution and a 0.2%, sorry, not molar, a 2% sucrose solution separated by a membrane permeable to sucrose. So imagine you have this, and there's a membrane here, sort of like the baggie. Now, what they want to know is which way the water's going to go, not which way the sucrose is going to go. So we're going to pretend like the sucrose cannot pass. So this is the 0.5% sucrose, and this on the other side is going to be our 2% sucrose. But we're pretending like, just like how the starch couldn't pass in our lab, we're pretending like the sucrose can't pass. So this has a higher concentration of sucrose. Now, if sucrose could pass, we know that sucrose would go this way. It would go from high to low, right? Because sucrose is a solute, and diffusion of any solute will be from where there's more to where there's less. However, we're pretending like the sucrose cannot pass. So we're going to get rid of that. We're going to get rid of that. So what will happen if only water can pass? And this is where people need to think about it, because it's not hard, but here's the deal. Water's going to go from where there's more water to where there's less water, but we don't see water in this diagram, right? But we can figure it out, because a solution is only two things. It's a solute and a solvent. Well, our solute is sucrose, and that's 2%. That means the rest of our solution has to be water, so our water is 98%, and that would give us 100. Now on the other side, we have a 0.5 molar sucrose solution. You'll learn about molarity in chemistry. I keep saying molar percent, which means it's 0.5% sucrose, and that means how much water? 99.5% water, because that's going to add up to 100, our solute and our solvent. So the question is, which way will water go? Well, just like anything else, water will go from where there's more to where there's less. Well, 99.5 is a bigger number than 98. So we would expect the water to go to the right, and the water level on the right would actually go up, and the level on the left would go down. So that's how you're going to solve these problems. See, this is showing the same thing. Notice how we have a much more concentrated solution on the right, a lot more dots, and they're saying only the water can pass. Which way is the water going to go? It's going to go towards the side with more solute, because that's the side that percentage-wise is going to have less water.
Osmosis.
Sorry about that. So there's some words for this. Tonicity. Tonicity is a word that describes the ability of a solution to cause a cell to gain or lose water. It has to do with which way is water going to go. So cells will usually shrink in a hypertonic solution. They will swell in a hypotonic solution, and they will stay the same if they're animal cells in an isotonic solution. However, plant cells will actually shrivel up in an isotonic solution. So let me explain why. So hypertonic means more concentrated or more solute. Hypotonic means less concentrated or less solute, and isotonic means equally concentrated, so equal amounts of solute. Water will always go towards the more concentrated or hypertonic solution and dilute it. Why? Well, because, remember, if we redraw our picture, which side is hypertonic? So let's take a look at this. So side A, if you remember, was 0.5% sucrose. And side B was 2% sucrose. So which side is more concentrated is side B. So this side is hypertonic because the hyper and hypotonic refer to the solute. So this side is hypertonic and this side is hypotonic. But the sucrose can't move. So the question was, which way will water go? Well, if you remember from our problem, if we calculate the amount of water, this side was 99.5% water, and this side was only 98% water. So we decided that the water would go this way. Well, isn't it true? That means the water's going towards the hypertonic solution because it's going to dilute it so that this percentage of sucrose would go down and it would sort of even out. All right. Now, osmotic pressure is the push on that hypertonic side where the water's sort of pushing through. Now, what we're going to do, so tonicity, the measure of the amount of substance dissolved in a liquid, typically it's water. So let's take a little practice question. Assume this membrane is only permeable to water. Which side of the membrane is hypertonic? Well, remember, hypertonic means more concentrated, meaning more sugar. So the side with more sugar, the red dots, is this side. So this side is hyper. This side is hypo. Which way is water going to go? Well, we don't actually have numbers here, but if you just memorize, water's always going to go to the hypertonic side because that's the side with less water. Since it has more solute, it has less water. The water will go to the left. The level will go up here, and the level will go down here. And look what happens. So the water went this way. Now, even though you didn't have numbers, you should still know water's going to go to the side that has a higher concentration of solute. If you had numbers, you could actually calculate the percentage of water, and you'd know that water's going to go from where there's more water to where there's less water. But remember, if I count the blue dots, there's way more blue dots over here. That's our water. There's a lot less over here. All right, here's one more. So only water can pass. So in A, it looks to me like there's a lot more solute, the dissolved particles, inside the cell than outside. So that would mean my inside is hyper, my outside is hypo. My rule is water is always going to go to the side that's hypertonic, because that's the side with less water. It has more solute and less water. So in this one, it's hypertonic, hypotonic. Water's going to go in. Now let's look at 2. We've got kind of like the dots are exactly spread out the same on both sides. So this is isotonic. Water will go both directions equally in an isotonic solution. Don't say water won't move. You're going to get it wrong on a test. That's really important. It doesn't stop moving. It's not like the water actively looks across to the other side and says, hey, buddy, you got the same amount as me. Let's just stop. Water's randomly moving around. But if the amount of water on each side is equal, the chance of water going this way is equal to the chance of water going the other way. And so we would say that water will go both ways equally. And this cell will stay the same, by the way. This cell, hypertonic, this cell might burst. It'll definitely swell up and it might burst. But, and this was the thing about the plant cell, it was talking about plant cells a couple slides back, plant cells won't burst. Plant cells will just become really firm. Why? Because of 2 things. Number 1, remember plants have a giant vacuole that stores water, and they have a cell wall. So a plant cell will actually look the healthiest when it's in a hypotonic solution and the plant cell itself is hypertonic. That will actually create pressure. If you put a plant cell in an isotonic solution, in an animal cell, that's good. It'll stay the same. Our blood is in an isotonic solution, so our blood cells stay the same. But if you put a plant cell in an isotonic solution, it's actually going to look kind of wilted because there's nothing to create pressure against the cell wall. Excuse me, like it does here where the vacuole creates pressure, and so the plant will actually look wilted. And now in our last one, so now we have more solute outside. So outside is hyper, inside is hypo. This cell will shrivel up. And that would be a plant or an animal cell, both. They would shrivel up because the water would leave. It would go towards the hypertonic side. All right. Next time we're going to talk about how cells cope, but I do want to show you very quickly a couple of practice problems. So we were doing a worksheet in class, so in case you were absent, I wanted to show you a couple of practice problems. So on these, they give you the solute. Let's just do these three. They give you the solute and the water on each side. They want to know, is the outside hyper or hypo or isotonic to the inside? So let's look at this first one. So to figure out hyper and hypo, we look at our solutes. There is less solute outside compared to inside. So that means outside must be hypotonic to inside. And technically inside would be hyper. I did not make you guys label that in class, but just a heads up, if one side's hypo, the other side's hyper. Now the second question is, now that we know the outside is hypotonic, which way is water going to go? And you were supposed to draw an arrow. Well, water's going to go towards hypertonic, but in this one, you also can see, literally see, the water levels on each side. So that means that that you could just say that, oh, I remember, water's always going to go from where there's more to where there's less. So water should go in because it's going towards where there's less water. But you could also just memorize that water's going to go towards the side that's hypertonic. Let's look at the second one. So look at our solutes. 37% out, only 10% in. So outside is hypertonic. I'm just going to write hyper. Inside would actually be hypo. And which way will water go? Well, water always goes towards the hypertonic solution, so water will go out. But you can also use the water to figure it out. Water's going to go from where there's more to where there's less. Now remember, if the solute could pass, it would also go from where there's more to where there's less. In other words, in this first scenario here, the solute, if it could pass, would go out from 55 towards 25. But we were pretending in this worksheet, it said that only water could pass. Let's look at our third one. 50% solute out, 50% in. So this is isotonic on both sides. And that means water would go both ways equally. That's really important. It doesn't stop. You wouldn't just draw no arrows. It would go both ways equally. All right, now the second page of this was missing stuff. So I'll just do a couple of these, and then we're going to run out of time here. So this one, let's look at this one. They don't have how much water. Well, how do you figure that out? Well, remember, the solute plus the solvent have to add up to 100%. So if this is 15, the water's 85. And then outside, these also add up to 100. So if this is 80, then this is 20. Now we can figure out, is the outside hyper or hypo? We look at our solute. Our solute is higher. Hyper means more solute. So this is hyper. And inside, of course, that means is hypo. Water always goes towards the hypertonic side because that's the side with less water, right? 85, only 80. Water will go out. All right, one more really quick. Inside, we have 39% solute. So that's got to add up to 100. So that's going to be 51%. Is that 61%? 61%, sorry. Can't add in my head. All right, 61% water outside, inside, and 39% solute. Outside, we have 20% and 80%. So we look at our solutes. Our outside has less solute, so it's hypotonic, and that means water should go towards the other side, right? Because it's going to go away from hypo and towards hyper. But we can also look at our water. 80 is higher than 61, so water should go into this cell. All right? So that's how you solve these. For the tonicity, you're going to look at the solute, height,